Okay, let's get started. This is Bob Dever. I'm the VP of Marketing at ScyllaDB, and I'll be your moderator today. And I think just about everyone who has joined us this morning knows that over the last decade, the drive for real-time stream processing has seen Kafka spread to tens of thousands of companies, including the majority of the Fortune 100. And in roughly that same time frame, we've also seen the rapid adoption of the NoSQL database with its tremendous scalability and the potential to handle massive workloads in real time. And it's no surprise to see these technologies used together. Certainly at ScyllaDB, we see a huge number of our users are also using Kafka and Confluent Platform. So in this webinar, we'll talk about the intersection of these technologies with a focus on the combination of ksqlDB and Scylla. And I'm glad to introduce our esteemed presenters today, both of whom have impressive track records in this industry and related fields. Hojat Jafapour is a software engineer at Confluent, and he's the creator of ksql, the streaming SQL engine for Kafka. He's got his PhD in computer science from UC Irvine, and Hojat has also been a speaker at our Scylla user conference multiple times, so we're glad to welcome him back today. Mahi Quinturu will start things off today. He's a solution architect here at ScyllaDB, where he works closely with our customers to ensure their success with our database. Mahi holds a master's degree in electrical and computer engineering from the University of Texas at San Antonio. And in addition to all the other things he does at Scylla, Mahi is our point person on all things Kafka. And with that, I'll hand things over to Mahi.
Thanks, Bob. So here is a brief agenda for today's talk. First, we'll begin with a high-level overview about ScyllaDB and the open source framework, C*, on which Scylla is built on top of. We will also briefly touch upon some new features and how customers can take advantage of them. Next, we will dive into Apache Kafka and the various Confluent Platform components like Kafka Connect, ksqlDB, etc. We will then explore some joint use cases based on customers and prospects who use Kafka and various NoSQL solutions across domains. Towards the end, we'll take some questions. Please post your questions as and when you get them. A little bit about ScyllaDB and our product Scylla, the real-time big data database. Scylla is a highly performant, low latency, scalable, and autonomous NoSQL database, which supports both Apache Kafka, Apache Cassandra, and Dynamo API. So the same client drivers and application code written on top of Cassandra or Dynamo are compatible with Scylla without any code changes. Scylla has three offerings: Scylla Open Source, Scylla Enterprise, and Scylla Cloud, which is a fully managed service. We also support the option of running Scylla Cloud in customers' cloud account. We are founded by the creators of the KVM hypervisor, which, as some of you might know, is an open source virtualization technology that is built into Linux. ScyllaDB, the company, has about 100 employees located in more than 15 countries across the world. We are expanding and currently hiring C++ and Golang developers and DevOps engineers. Now let's spend some time understanding some of the basic design principles that differentiate Scylla from other NoSQL databases. Scylla is written in C++, which results in faster performance, lower latencies, and efficient use of the hardware. Scylla has a shard per core isolated architecture, where each Scylla shard is associated with the CPU core, and the necessary RAM is allocated by shard as well. This ensures we are never starved of resources. Everything is async on the platform, so there are no locks. Scylla also runs on XFS, so we get the performance benefits of using an asynchronous file system as well. Scylla comes along with a cache, which is highly optimized and auto-tuned to your workload. So no need to worry about key caching, row caching, Linux caching, on-heap, off-heap caching. Everything is auto-tuned. Scylla is built on top of an open source framework called C*, which orchestrates both task I/O and disk I/O scheduling. We will get into this a bit more in the next slide. Scylla is an autonomous database, which means your administrators get the benefit of minimum tuning. As I mentioned before, Scylla is built on top of open source framework called C*. The framework understands that there are essentially 5 different kinds of backend operations: commit logs, mem tables, compactions, queries, and repairs. These individual operations are scheduled through the C-star scheduler. So in effect, the C-star scheduler moves the scheduling out of the kernel space into the user space, where every request is parallelized and given its own priority. Also, when you install Scylla, it tunes itself according to the disk, RAM, CPU available, and network made available to the server. This, in effect, makes the database autonomous. Scylla's users benefit from Scylla's full compatibility with Cassandra and the Cassandra ecosystem. All of the ecosystem components listed here and many more just work out of the box with Scylla. In addition, there are many client drivers available in a variety of programming languages that can be reused as well. Scylla has created various optimized drivers for developers using Java and Go. These optimized drivers can better take advantage of the internals of Scylla Enterprise as well as Scylla Cloud. We recently released a new feature called CDC, or Change Data Capture. Change Data Capture logging basically captures and keeps track of data that has changed. It can also help with mirroring your database, and also replication and state propagation across various microservices. So you basically get a lot of help because of CDC, incorporating CDC into your architecture. It is configured per table, with limits on the amount of disk space that's available to consume for storing your CDC logs. We also co-locate these CDC log partitions along with the base table partitions, as it greatly improves the performance. There are a variety of configurable options, subscription options that are available to configure the stream of the change log. You can choose to have either the post image, that is the change state, or just the delta, that is the changes made to those columns, or you can also stream the pre-image, that is the previous state. Feel free to refer the link I pasted below for more information. We're planning on releasing CDC Scylla Kafka connector, source connector, which overall makes it easier for developers to build globally synchronized services. This also significantly reduces the amount of data to be moved and provides a reliable way to stream the data between various systems. Now let's dive into Kafka and the Confluent Platform. Rajat, on to you.
Thanks, Mahi. Hello, everyone. I will give you a quick overview on event streaming platform, the Confluent Platform, and then I will dive into more details on ksqlDB. Next slide, please. So the main goal of event streaming platform is to simplify this complex architecture that we see here. A lot of businesses have different lines of business, and they have complex systems managing those lines of business. And previously, before the streaming world, if you wanted to use these different systems in conjunction to each other, you would end up with an architecture like this, that a lot of different parts of these systems had to communicate with each other. So the main goal of event streaming platform is to fix this kind of architectures and become the central nervous system of any enterprise, to make sure that the data exchange and communication among different components go through the central place and simplify this architecture. If you go to the next slide, we can see a general overview of the event streaming platform. The event streaming platform, you are going to have universal event pipelines from different systems. Data is going to be generated by producers, and a lot of components are going to consume this data. And this architecture decouples the producers of the data from the consumers of data, which makes it much easier to design systems around consuming and using data for different purposes. And also you can have contextual event-driven applications. These applications react to the events as they are happening, and it significantly improves the functionality of any business. So assuming that you have the event streaming platform as a central nervous system of your system, let's now dive into the event streaming platform and see what components we have inside this platform that simplifies your architecture. Let's go to the next slide, please. So the main component in the event streaming platform is Apache Kafka in Confluent Platform. Apache Kafka is a distributed commit log. It provides a publish, subscribe, streams of records for producers to produce these streams of records and consumers to consume them. It's highly scalable and it is fault tolerant. It is battle tested, and we have a lot of users that are using Kafka in extremely huge scales. And this builds the backbone of the many streaming platforms that we see in businesses right now. But in addition to the core Kafka component, the streaming platform has more components that builds on top of Kafka. If you go to the next slide, one of the main components on top of Kafka is Kafka Connect. This is part of the Apache Kafka project and also part of a Confluent Platform. Kafka Connect API provides a way to bring data into Kafka and take data outside Kafka to third-party systems. As Mahi said, Scylla and many other systems can be source of data that you can use a source connector to bring the data from those systems into the Kafka topics. And then you will have consumers that would be able to use these data without the producer have to know about who's going to use this data and when. And also we have sync connectors. Imagine you have the data in Kafka and you want to take it to different systems that you have. Again, you can use sync connectors and easily move data from Kafka to these connectors, to these third-party systems. And as you see, Kafka sits in the middle and all of the communication can go through Kafka, and this decoupling significantly simplifies the architecture of your system. The third part of the Kafka ecosystem here, if you go to the next slide, is Kafka Streams API. Kafka Streams provides a stream processing framework on top of Apache Kafka. So you can process the stream of data as the data arrives in these streams and take action depending on the application you have. Kafka Streams in the Kafka ecosystem is a library that you can import and use it in your applications and also in microservices that you have. So let's dive a little bit more into the stream processing in Apache Kafka ecosystem. If you go to the next slide, I'll give you just a quick analogy about how you can think about stream processing. So imagine in normal Linux shell, you can easily write a simple pipeline that you read data from a file, do a processing on it, and write the results into another file. You can easily imagine this in a Kafka applications. You can read data from different systems and bring it into Kafka topics. In this case, Kafka Connect API will be the analogous analogy that we use here. Then you can do the stream processing that you can use the tools that I'm gonna talk about later in later slides. And then you can move the results to the destination. In this case, we're having a file, but in case of Kafka, you can send it to any other third-party system that's we have sync connector for it. Next slide, please. So there are different ways of doing stream processing in Kafka. And in this diagram, I'm going to show you the differences between them and how you can decide which one you need to use. If you want the most flexibility and you want to be able to have highly customized application, consumer producer is the way to go. It provides an API such as subscribe, poll, send, and flush, and other APIs that we have for Kafka consumers and producers. But the difficulty is that you have to write the code yourself and manage all of the lifecycle of your applications. Kafka Streams, in the next slide, alleviates this problem by pre-implementing a lot of those common functionality and providing you with a domain-specific language that simplifies the stream processing app significantly and still gives you a flexibility of doing a lot of complex processing. On the other hand, still you are supposed to write your code in Java or Scala or language like this. But the last component that we see for stream processing in Kafka is ksql that provides ultimate simplicity, I would say, in this case. You don't need to know any programming language other than SQL. You can express your stream processing logic in SQL statements. We have some additions to those SQL statements to bring the stream processing concepts to the normal SQL language. And with that, you're able to write stream processing pipelines very easily. But on the other hand, it is not as flexible as the other components because you are limited to express your logic in SQL language, although we do have UDFs, UDAFs, and UDTF support in ksqlDB, but still you are bounded to write your logic in SQL. So in some cases, you may need to, if you have a super complex application that cannot be expressed in SQL language, you may have to use combination of ksqlDB and Kafka streams together. Next slide, please. Okay, let's dive a little bit into what ksqlDB is and what you can use it for. It's an event streaming database purpose-built for streaming applications. Streaming applications are the application that you are processing a stream of data as the data comes and you're reacting to it in real time. So unlike batch that you wait until you have a set of data and then start processing, in streaming you continuously process the data as it arrives. So it significantly changes the paradigm of how you use data and how you react to the data. And it makes it even more useful for businesses because time is essentially money. And if you can react to the events in real time, you can actually make much smarter decisions and benefit the business. ksqlDB enables stream processing with zero coding. As I mentioned earlier, you just need to know, if you consider SQL as no coding, you just need to use SQL language and you don't need to have any coding environment and deployment considerations. Everything is handled by ksql for you. It is built on top of Kafka streams and Apache Kafka, so it kind of inherits all of the good characteristics of those systems. Fault tolerance, scalability, it can easily scale out, scale down. It is a battle-hardened system because this Kafka is battle-hardened system. And it significantly reduces the complexity of event processing for you. So you take advantage of all of the good features of Kafka, but you can do it simply with SQL language. Next slide, please. So let's see a couple of examples. These are just samples. We are going to deep dive into a couple of use cases later, but you can use it for streaming ETL. Imagine you want to have, you have a Krieg stream data stream that you want to enrich it with more information about the user. You can easily write a single liner to enrich the stream using the user information by joining it with a user table. This can be done continuously. So anytime you have an update in any information about the user, if their level changes, it is going to be reflected in the output of the stream. Next slide, please. Another use case that you can use it for is real-time monitoring. You can easily ingest logs. We are going to have an example of this, and continuously monitor the logs and define criteria to notify or to take action continuously in real time. And this one-liner can easily show you how you can, for instance, do aggregations and react for the specific criteria that you can define in your statement. Next slide, please. So ksqlDB has a lot of features that makes this stream processing simple for you. We do have aggregations, we do have window aggregation. You can define different types of windows. Supported windows at the moment are tumbling window, hopping window, and session windows. We have a variety of joins. You can join two streams. You can join a stream with a table, and you can join two tables together. And each of these joins, again, are being handled by Kafka Streams applications, so you inherit all of the scalability, fault tolerance, properties of those. We support nested data, the struct data type. We have user-defined functions for applying to each single row. You have user-defined aggregate functions, and recently we added user-defined table functions that you can read a row and emit multiple rows above. We have different data type support in ksqlDB right now. Avro, JSON, and CSV already are there. In the next version of Confluent Platform, we are going to add protobuf support using the schema registry. And ksqlDB has two new features that at the moment they are in preview, that are being able to query the state store for your aggregate queries, and also integration with Connect that you're going to see some examples from it later. Next slide, please. Now I'm going to have Mahi to explain some of the use cases that you can use Scylla and Kafka and ksqlDB in conjunction.
Thanks, Ajay. So based on a number of customers and prospects who use Kafka and various NoSQL systems, I'll walk you through a few use cases that are relevant for ksqlDB and CDC from Scylla and Kafka. Some of the examples we're going to be talking about are like how to detect SSH attacks, IoT, smart home use cases, customer 360 use cases, and network and endpoint security type use cases. So here's a simple use case where we have access to certain logs, let's say syslogs, and now we need to detect if there are any brute force SSH attacks. You want to see the results in Scylla and point your monitoring to it, and also, let's say you want to try Elasticsearch and do some ad hoc analysis on top of this data. Here is a sample architecture which you could use. Syslog is basically built into Linux, and it also it's common in networking and IoT devices to stream the log messages along with the metadata such as the source host or the severity of the message payloads or tags, either into a local log file or a centralized syslog server. Here in this case, let's stream it into Kafka. You could use the simple source connector, and it can be done with this simple one-liner. So data gets automatically streamed into Kafka, which makes setting things up a lot easier. Now let's also set up the Elastic sync. You could set all of this up using this one-liner and push it into Elastic using this sync connector. You could also use the sync connector for Scylla. By the way, I mean, all these are still in release. I mean, they're about to be released pretty soon, and they're still in development. But right now, JDBC connectors are natively supported. Rest all are going to get added soon. So this is how you would set up a Scylla sync. You would define the connector classes and also the topics you want to from which you want to stream it into Scylla, and also the key converters which you want to use. And so now we have established all the necessary connections, and if you want to do a few simple ksql queries, we can start working on this data. To begin, let's create a stream of syslog, and that's what is there in the first command, which reads from the topic syslog. Then you can browse through the data. It already has the necessary schema. It's already connected to schema registry. Now let's join it with the facility table, which adds a little bit more information into it. Like it enriches the data regarding various, so let's say you have some various message levels. Message 0 would indicate a kernel message. Message level 1 would indicate a user level message, and so on. After you have joined this data, so you run this simple left join on top of this data, let's filter the messages which contain only the invalid SSH attempts. As you can see in the query, you can filter out the messages which contain the invalid user log error, as this indicates that there was a failed SSH attempt. Then let's create a stream of such messages. You can do a bit of reorganizing of the data using the split and rebalance primitives. Now, if you want to persist the query, you can simply create a table based off the stream. This is what Rajat was explaining before. It's about the stream table duality, which you can interchangeably use. There are basically two ways to interact with this data. You can create either a push query or a pull query. If you look at the push query, when you create a table which is fetching data from the stream, the data gets pushed into the table automatically. That would be a push query, or you could also look for specific data and request a pull query from it. So let's discuss another use case. Smart home and IoT use cases. Smart home and IoT ecosystems are becoming very popular. For example, even in my home, I have about 15 to 20 connected devices that are active at any point in time. There are typically three parts to this connected ecosystem. There is the smart hub, to which all the devices are connected to, and then there is the mobile, which can control all the devices, and then there is the cloud, which keeps track of the state of the hub. It keeps track of the state of the hub and other various devices also which are connected to it directly or via the partner network, various services which are enabled through it. The mobile typically connects and controls all the devices, but the orchestration of these is done through the cloud. Let's go through an example architecture here. So if you were to put your smart home, let's say in away mode, then all your lights need to be turned off, your doors need to be locked, and the air conditioning needs to go into echo mode, and the cameras need to detect motion, etc. The state of all the devices that are connected to the hub is typically monitored in the cloud. The devices which are attached to the hub are automatically moved to the corresponding state. And all of this is communicated from the cloud to the hub. This communication can happen via multiple protocols, CoAP, MQTT, or TCP. For this example, let's assume it's communicated via MQTT. And here is some sample code which can orchestrate all of this. You could possibly use the MQTT proxy, which is available as part of the Confluent Enterprise, and the data, once it comes into Kafka, can be automatically transformed into an address schema, and you should set up the necessary sync and CDC connectors to Scylla or Scylla Cloud. So now the data regarding the change of mode of the hub gets streamed into Scylla directly. And this change is detected by CDC on the Scylla side, and then it propagates the state to the few topics, the corresponding topics. So ksql then picks up this change and runs the stream join operations, as you can see listed here on the right side. And these join operations combine the data of all the devices that are connected with the hub with the lookup table, which contains the final state that these devices need to be in. And this state of the devices can simply be communicated back via the MQTT proxy. So the entire end-to-end architecture could just be orchestrated by these few simple lines of code. Actually, not code, but just SQL statements. Now let's dive into another use case. Let's say that you were pushing out a new release of your product and you would like to track various customer issues or assess your support level and eventually propagate this to your customer 360. There are a number of ways to do this, but calculating CES or customer engagement score is one easy way to find out. And once you do that, you can keep your customer 360 portal up to date as well. So you can, an example architecture for doing this would be, you can start off by logging all of your customer interaction data into Kafka from your application, or you could persist it into MySQL instance directly. If you enable CDC on this data, then basically the necessary changes from the customer logs tables are streamed out into Kafka. Now, by simply running the ksql queries on top of this data, you can find out the number of issues organized by customer. You can find out the number of, you can list them out by the number of touch points per incident, per ID. Also, you can set a quality of service level, wherein you want to track issues that have received repeated calls from the customers on the same incident over and over the last 24 hours. Let's say you define that quality of service level. And all of these can be simply achieved by these three queries here, where you could do count distinct or even count operations on this, and you should simply be able to get your and this can be easily propagated into your customer 360, where you have data for your long-term storage. Now, let's jump into this new use case. let's assume that we're collecting syslog, netload, DNS, and firewall logs from all the devices that are connected to your internal corporate network. These could be from devices like your mobile phones, laptops, routers, switches, servers. Using these logs, we need to identify the higher risk endpoints that could possibly be compromised. This is typically a very high throughput use case, and this type of risk analysis can either be done in real time or done as postmortem analysis for an incident response. After identifying the bad actors within the network, the sysadmin would typically remove the compromised endpoints from within the network. To implement this usually involves a lot of complexity, and IT infrastructure also needs to be set up. Let's explore how we can simplify this. So the data from all these various endpoints is streamed into Kafka using the sync, and then using the sync connector pushed into Scylla. Now, using the ksql stream join, you can combine these various streams to derive a risk score. And ksql can provide a rich set of SQL-like primitives, but sometimes you might need to create your own custom machine learning algorithm, and oftentimes very specific to your own solution or your own product. And also you want to make this available to your business analysts or data scientists who want to do some ad hoc analysis on this data. In this case, we can derive the risk score by combining the data from different streams. And as you can see, the derived risk score is a UDF that you've defined, which takes the data from multiple sources and gives out a risk score. You can simply use this UDF as part of your regular ksql. And here I pasted a link where you can go in and understand how to build your own UDFs as well. Once we calculate this risk score, we can order them by descending order and simply pick the endpoints that are crossed a certain given threshold. This will trigger a monitoring alert for the sysadmin who can then look into remediating the risk. Okay, so to summarize, here are some takeaways from today's webinar. ScyllaDB now supports change data capture, or CDC. ksqlDB provides a SQL interface for streaming applications. ksqlDB is essentially, it's a very easily extensible framework for your custom UDFs. Scylla has a sync connector, and the CDC source connector is coming out soon. Here are some Scylla resources that you can use for further your understanding. These slides would be sent out as a follow-up to the webinar. Feel free to go over them. And in the same way, here are some Confluent resources, which you could use them as well for furthering your ksql and Kafka knowledge and the Confluent Platform knowledge. And there's and there's a Kafka Summit coming up as well. There's Kafka Summit in London in April 27 and 28 of this year. And there's a Kafka Summit in Austin this year, which is getting organized, which is on August 24th and 25th. And we will be available as well. And Scylla is a sponsor, and we would be available as well. Feel free to drop by. So now it's time for Q&A. Just if you have any questions, feel free to ask them. And on to you, Bob.
Thank you, Mahi, and thanks, Ojat. And as Mahi said, yeah, we'll take your live questions now. In fact, we've already received a number of really good ones. I'll say it again, we'll cover as many of these questions as we can get to today. We have a pretty large online audience for this webinar. So if we don't have time to answer your questions during the webinar, we'll follow up with you shortly thereafter. Mahi, I'll start with you. Here's one. It's two questions from the same person. So the first part is, I'm a MySQL user. How do I export my existing data into Scylla?
Yeah, that's often, I mean, it's an increasing trend which we've seen where, folks from MySQL, like as and when your application tends to grow, you have a lot of growing pains. You have to go and reshard, and you have to be able to scale your cluster. It oftentimes requires a dedicated effort. If you were to move it into a NoSQL system, a lot of this pain tends to go away. And typically, there are multiple ways of doing this. CDC is a very, very useful way to stream your data out of MySQL. You could also import this data into a batch processing system and try to change or massage the schema and push it into Scylla. But Kafka would be the preferred approach to migrate this data. And do engage with us. We have a lot of experience doing this.
That's great. That's a great segue to the next question from the same participant. How is CDC source connector different from MySQL connector?
So CDC is a very general, broad concept, and every database tends to have its own CDC. Connect source connectors, or that's how you would stream the data. Or there's also Debezium, which is an active project where a number of databases are connected with it. So you can stream out the changes from your database, and you can send it into a Kafka-like system, which can then have subscribers, which pushes it out to Scylla, or any NoSQL system for that matter. And so typically that's how you would need to look at this. It's Scylla's. We tend to believe that Scylla's CDC source connector is also very highly performant because of a number of optimizations that we have done to how we've architected it. But CDC is in general broad concept which every database is beginning to support.
That's great. Thank you for that, Mahi. Hoja, we've got a number of questions for you. I'll start with this one. I'm already using ksql. What are the additional benefits of using ksqlDB?
Well, ksql and ksqlDB essentially are the same thing. And the only extra features that we have in ksqlDB are the ability to query the state store for aggregate queries and integration with Connect. So in a sense, ksqlDB is the continuation of ksql. So we are rebranding a ksql to ksqlDB, and from next release or so, we hopefully are going to have just one product, which is ksqlDB. And those two features, as I mentioned, at the moment they are in preview, but hopefully soon they're going to be ready to use in production too.
That's great. Thanks for that. Here's a related question. I'm already using Spark SQL and Kafka. What are some of the benefits of using ksqlDB, and would I be able to replace my Spark SQL with ksql?
Well, that's actually an interesting question. It depends on many factors, but let me give you a main difference between using ksqlDB and compared to Kafka. Compared to Spark. The main thing is the execution model. So in Spark, you have a cluster that you need to manage it. In ksqlDB, we are using Kafka streams underneath. So you have the option of using a cluster, or you can integrate it into your application and just bring up the nodes, instances that you need. So from the operations point of view, you don't have to manage a new cluster compared to Spark or other systems that you need to have another secondary cluster in addition to Kafka. So I would say that would be the main differentiation. But if you are performing processing using Spark SQL, I would say with high probability, it should be very easy to port it into ksql, and you may have to do some customization on your queries and statements because of the differences between ksql statements and Spark SQL statements. But other than that, you shouldn't have that much difficulty to convert and try ksql.
That's great. Hey, we've got a number of Python-related questions. So I'm going to try and lump these together. The first was, isn't coding in Python possible to create Kafka pipelines? Is Java the only way? Is one. And then What was the other one? We had another one. Well, I'll start with that one, and I'll track down the other question.
Well, if you want to just use Python to read and write to Kafka, I assume we have a Python client that you can use that. And for performing any processing, you can write the processing logic in Python yourself. If you remember the slides that I had, producer, consumers, Kafka streams, and ksql. So Kafka streams at the moment, you can only use Scala or Java. It's a JVM framework, but you can also use ksql from your Python application by using a REST API that we have for the ksql cluster. So you can submit your queries from the Kafka, from Python applications. But in general, if you want to do any serious Kafka stream processing in Python, I would say sticking with the consumer producer API would be the first step.
Okay, that's great. And the other question that is very related, I think you've addressed this, is there a connectivity between Python and ksql using Apache Kafka?
What do you mean by connectivity? As I mentioned, you can use the ksql REST API to submit queries. Note that the ksql and Kafka Streams applications, they read from Kafka source topics, perform processing, and write to another Kafka topic. So technically, your input and output are going to be in Kafka, and you can submit your statements through REST API from Python or any other language, and then you can read the results of those processing, again, using a Kafka client from those languages, including Python.
Thanks. Here's a question for Mahi. What's the CDC output? My understanding is that it detects events and schedules actions accordingly. Is it similar to capacitor, but using Scylla tables?
Yeah, so CDC output, I think as I mentioned in the slides, like there's various subscription options available to the change log. You have basically the pre-image, which is the change before the delta was applied, and then you have just the delta, which was the change which got written into the specific table on which CDC has been enabled. And you also have the option of streaming out the post image, which is post the change that has been applied. And you have a configurable way to pick and choose between all these three, or if you want all three, you can. But you have to be aware, like, that now the necessary compute and the necessary in number of nodes which would require to handle all of these and give the appropriate SLAs. If you want to keep the SLAs between, less than, in a single digit milliseconds, or you want it a little longer SLAs. And if you want these little longer, then you can, all of this is asynchronous. It is not synchronous. So, and so if you have to make sure that the necessary hardware is supplied for all of this, so necessary compute is available. I'm not very familiar with what capacitor is, but so it's something. CDC is a generic concept, like how we've Debezium does it. It's an open source project out of Red Hat. So these are some options which you can use if you want to build on top of CDC.
That's great. Thank you for that, Mahi. Here's a question that just came in, going back to Python. Can you please share a document using Python with Kafka ksql REST API?
Sure. We do have the documentation for the REST API for ksql. You can refer to documentation page in Confluent. I don't have the link now, but I think a simple Google search should give you the link to the documentation for our REST API.
That's great. Here's a very straightforward, I'm assuming this is a question for you, Hojad. It says Kafka versus Confluent Kafka. And I'm assuming
I am biased on that one, but let me give you an example. Confluent Kafka is Apache Kafka plus a lot of IP on top of it. And it includes a lot of security feature, includes a lot of operational simplifying operations features and monitoring features. So I would say, if you have the expertise, you can try Apache Kafka. If you want to focus on your business and your applications and not worry about managing and operating Kafka, definitely take a look at Confluent Platform and also our cloud service.
That's great. Here's another question for you, Hojat. What is the difference between UDF, UDAF, and UDTF?
Great question. So it's kind of similar terminology that we have in normal databases, relational databases. UDFs are functions that are applied for single row and emit the single row. For instance, you can uppercase a field and it's going to be applied to every row and it's going to emit the results for every row. UDAFs, or aggregate functions, are functions that get set of rows and emit the results for them. For instance, sum or count. You have set of rows, but you have single output for them. Those are UDAFs. And UDTFs, or table functions, are the functions that get one input, one row, and emit multiple rows. Imagine unnesting an array. So if you have an array column, you can have a UDTF, that reads this single row and emits multiple row, one row per item in your array. So you can look at them as how many rows they read and how many rows they produce.
That's great. Thank you for that. I think we've got a lot of interest in machine learning in our audience today. Here's another Python question. Isn't coding in Python possible to create Kafka pipelines? Is Java the only way? I thought we asked.
No, you can use Python. As I mentioned, we have producer consumer in Python, and you can easily read and write data from Kafka topics in Python, and you can do the processing in Python. The only thing that you need to do is that most of the features that we have, for instance, in frameworks like Kafka Streams, you are implementing them yourself in Python. But definitely, there are ways to integrate Python and Kafka.
Great.
In the same way, I mean, can they be integrated with ksqlDB, and can they be UDFs, which we can create from Python?
No, at the moment, the UDFs only needs to be written in Java or Scala, but we have had this request. It's not prioritized yet, but hopefully soon we will have a way of writing UDFs in different languages other than Java and Scala.
Yeah, just a lot of machine learning related interest, basically.
Yeah, that's one of the use cases that we see quite often, especially in the case of ksqlDB. We actually have several blog posts from my colleagues about like how you can apply machine learning algorithms to your stream of data. And UDF, they do have UDFs that apply those algorithms to streams in ksql.
Here's another question for you, Hojat. Could you use ksql for scenarios like distributed transactions or rollbacks?
This is a very vague question. I don't exactly know what you mean by distributed transactions and rollbacks, but pay attention that this is a different paradigm. We are looking at stream processing. We are not looking at transaction processing in the way that, let's say, traditional relational databases are doing. So here you are reading stream of data, performing some processing, and writing the results continuously to output. So we do have concepts such as exactly one guarantees and exactly one processing, but I don't know how you can bring the transactionality of traditional databases. For instance, you have concurrency and rollback commit process for multiple transactions and those kind of things in the stream processing context.
Great. We have time for just one more question, and I'm gonna do one that just came in because I think it's a good one. I'll give it to you, Mahi. What is the advantage of using ksql using traditional databases like MySQL or MS SQL?
Yeah, I think both I can answer or Hojat can answer on this. ksqlDB provides a lot of flexibility, and if you want to be able to do streaming on top of this if you want to do compute, or some people say continuous applications on top of this data, ksql provides a really useful interface. And you can use your database for some long-term storage, or retrieving, or if you want to do range scans or things like that, you can use, I mean, not necessarily MySQL, you can use any databases in generally in terms of a NoSQL store or any relational store. But ksqlDB provides an interface for your streaming application. So as and when your data is getting streamed in, you want to apply real-time transformations to this data. That's where you would use ksqlDB. And if you want to migrate data out of this, or you want to mirror data, you want to transform data, you can use ksqlDB as well to do massaging the data and saving it back to a database. Hojat, feel free to add to that.
Yeah, I just add a couple of extra points to that. MySQL, SQL Server, all of these relational databases, mostly they are using store and query model, meaning that you store the data in tables and then you query them. So your data is static, not static in the sense that you do have changes, but your data is there and the queries are coming to this data. On the other hand, in continuous query systems like ksql, your queries are sitting there and data comes to these queries. So it's a different way of looking at it. So normal, traditional databases, you have data sitting there, queries coming to this data, and you get the query, get the results, and that query is done. In case of continuous query systems like ksql, you write a query stays there forever, and data keeps coming. As the data comes, query consumes that data and processes data and generates results continuously. So it's a totally different paradigm, the way that you process data in traditional store and query data systems compared to continuous query systems.
That's great. Thank you for that. We got one last question, and I'm going to answer it. The question is, can you send me the link for this recording? Yes, is the answer to that. We're going to send everyone the link to the recording and the slides. We didn't have time to get to all of the questions, but we will respond to you guys. We'll follow up with those answers. And I just want to thank everyone for joining us. We'll see you at our next webinar, and thanks to our speakers, Mahi and Hojat.
Thank you.
Be well, everyone.